Hey, welcome back. For the longest time I wanted to talk about small diameter boring bars, especially for the lathe but also for the boring head. There are many different options and I want to go into a few of those options and also show you how to grind a very decent solid carbide boring bar on the deep grinder, or if you have one on a tool and cutter grinder, or on a surface grinder for that matter. I have some options for boring out here, small diameter boring. The elephant of the room, of course, is insert tooling. Steel shanked boring bar. This is a 10mm shank with a CCMT insert. These are great. They're reasonably priced. The boring bar, depending where you get them from China, it costs about $10. If you get one from a reputable seller, it costs about maybe $70. You can get them with a solid carbide shank. Why solid carbide? Because it's 3 times stiffer than steel. That means if you clamp it back here, both a steel shanked and a carbide shanked boring bar, and you put X amount of load on the tip of the tool, the full steel body tool will deflect 3 times more than the carbide tool. That means carbide will work with longer stick out. But on the lower diameter side, insert tooling has a limit. I think the smallest inserted boring bars that you can get start at 4.5mm bore diameter. And those are really tiny. The inserts are tiny, the insert screws are tiny, and everything gets expensive. Usually for me, insert boring bars start at a bore diameter of roughly 8 to 10 millimeters. And we have this style with the round shank. These are high-speed steel. These 4 here in the center. Let's get this out of the way. These are made by Comet, Eifanger, Hoofnagel, and some more. And these are great. Round shank, solid high-speed steel. You can get them with carbide heads too, silver braced on. And you grind them here on the chip surface and you just rotate them into the grinding wheel, and you can regrind them forever until nothing is left anymore. But if you regrind them wrong, you butcher them up really bad. And these start at really tiny diameters. This one can go into a 3mm bore without a problem. Not very deep though. I don't use them very much anymore because they're high-speed steel. And if you work with a lot of tool steels, you burn them up quite fast, or you have to go slow as can be. And then we get into solid carbide territory. A very common system here in Germany is from Paul Horn, this boring bar system with the teardrop shaped shank. These are solid carbide, have this shank, have a through hole for through coolant, which you can actually use on a manual lathe. I made these holders, at least this one here. I milled the profile, the teardrop shaped profile on the CNC down into the shank. So these tools can go in if you unscrew the screws far enough. They drop in. And the reason for this teardrop shape is so, especially on a CNC machine, they're indexable or repeatable. You take them out if it's dull or broken, and you replace it, and you tighten down the screws with the same torque as before, and the tool is very much in the same position as before. Only very minor adjustments are needed. On a manual machine, that's not very critical. This holder is the same, only that it's drilled through, all the way through, into the tip of in the bottom of the teardrop profile here, and I can screw in a pneumatic fitting back here, and I can run air through the holder and through the cutting tool, and that's great for getting chips out of small bores. They would otherwise rub and scratch the surface finish. You can also run, of course, coolant through it, or you can hook up something like a fog buster or a Noga mini cooler, something like that, that gives air coolant mist through the tool. Works great. The drawback of this system from Paul Horn is it's expensive. A single boring bar of the system costs about, I think, 25 to 30 bucks, and they break easy. You can't break them, but you can get them used on eBay for very little money. You can, if you search around, you can pick them up for $1 a piece, €1 or $1 a piece, not a problem. And they're easy to resharpen. You just approach them at the correct angle, freehand on a diamond wheel, on front and top surface, and you're good to go again. I reground these a million times. That's why some of them look very, very weird. You can get them in different shapes. This one is 60-degree threading. This one is for an ID clip groove, and these are just standard ID turning tools that can go up to the shoulder and even face the shoulder. Very nice tooling system. Paul Horn tooling is absolutely high quality, no doubt about that, but it's expensive. And you have to either buy the holder or make one yourself. They're relatively simple to make. You just have to measure the included angle of the teardrop shape, drill the ends larger because there are not relevant surfaces, only the taper is relevant, and mill out the angle between them. It can be done on a manual mill or on a pantograph machine or on a CNC. This is another system. I think this is from Eifanger. I have no idea. These are also solid carbide. Nice boring bars. These are also tin titanium nitride coated, and these are also meant for CNC use, so they have a way to index them when you change them. Because of the round shank, you could set them up like this, like this, like this. But they have the large 30-degree chamfer back here, and the holder that these go into have a pin on the end, and you push the tool in, and this chamfer registers itself against the pin in the bore, just like this, and aligns the tool in the right orientation. It's a very clever and very simple system, and once it's orientated correctly, it's clamped. The holders are slit, and you just pinch them together with a screw and they hold the tool. So this is a very, very effective way to index round tools in a holder. So all of these are commercial options. Expensive, and reasonably expensive. If you can get used ones, these solid carbide boring bars are very reasonably priced. You can get a lot of work done with resharpened ones. I used them for years, and I only bought some of them once, and since then I used them. I have about 10 or 15 of these different shapes and forms, and I used them forever. But then but sometimes you want to be autonomous. This is a solid carbide boring bar that I ground from a 6mm carbide blank. In fact, it was just a broken carbide amp mill. And I just ground the front. It's almost ground like a D-bit, a single lip cutter for an engraver. Ground down to half the diameter in front here. Necked down this rear portion here, so it gets clearance when you go into a bore. I grind these on the D-bit grinder. It's very easy, but I realized when I looked at the commercial ones, they were basically done the same way. If you look at them, they are ground down to half the diameter in front here, necked down, and have a shank. but they're ground. The necking, the reduced diameter here is ground off center. That's for a good reason. I have to grind the diameter quite small to get a decent amount of clearance here, and that reduces the stiffness of the tool. If you grind it off center, like this one, it's only necked down on this side here, and here it's full material still. You get a lot of clearance by removing very little material. And that's what I want to recreate with my own boring bars that I'm going to grind in future. All we need is an eccentric bushing for the D-bit grinder that allows to grind this diameter here off center. This is what we're going to grind. This is a combination tool, one side end mill, one side boring bar. This is for mill turn CNC machines that can do both. As you can see, it's necked down off center. And this makes the tool relatively rigid, leaves a lot of cross section here, but also gives enough clearance here so we can resharpen this boring bar many times before it gets unusable. Preferably you regrind it on the front, so it just gets shorter, not smaller in diameter. It's ground to half the diameter here, and it has 20 degrees of relief here. This should work from a diameter maybe 7mm bore and up to this depth here, about here. So you could go 15mm deep with this one, and you just clamp it in a split bushing in a boring bar holder. And the way I ground this off-center neck relief here is just with a bushing, just a piece of 42 chromo 4 steel, 12mm diameter here, goes in a collet on the D-bit grinder, 0.75mm off-center, drilled and reamed 6H7. That's a close sliding fit for 6mm carbide. Carbide tooling or carbide blanks are generally ground slightly minus diameter, and it's drilled and tapped for a 3mm M3 screw here to clamp our boring bar blank for grinding. That's all you need. Okay, we're finally over at the D-bit grinder after a lot of talking, and I found a broken, chipped 6mm carbide end mill in my scrap carbide bin. One thing about the carbide used in end mills, usually it's a very decent grade of carbide. Micrograin carbide, relatively tough, has to withstand an interrupted cut, which is milling. And it can be sharpened extremely fine edge, and it holds the edge very well. So we take our bushing that we made earlier, get our blank in here, and we lock the tool down with the screw, just so it doesn't move. This lower joint here is at 90 degrees. That's a lie. It's at 0 degrees, and this upper here is at 0 degrees too. The indexing head here is also at an even number. In my case, I will turn it to 90, and I have a 12mm collet in here that matches my eccentric bushing. I drop the bushing into collet, and when you look full frontal onto the bushing, this screw indicates is exactly opposed to the throw of the eccentric. So we can eyeball our orientation. In my case, I will just line the screw up to be in a horizontal plane with the piece. So the eccentric is kind of oriented. And we set our indexing head to free spin, and now you can see that we have this eccentric motion. Now we have to decide what we want to grind. Let's say we want to grind a boring bar that can go down 15 millimeters in a bore and in a blind hole. If we mark 15 millimeters on the blank here, just like this, and that's how far we have to neck down the shank. And we will leave about 5 millimeters untouched in front here, which will be the cutting section of the tool. This here will be untouched, and this in between here will be relieved. It will, due to the nature of the eccentric, it will be relieved opposite to the screw over here on this side. For grinding, we will move the tool in. On this grinder I can move the workhead down here with the main axle axially in and out, but I can also move the grinding wheel in and out, which is very useful, and you will see in a second why that's the case. So we bring it in, and then we lock, and we have always this motion here, but we will lock it. So it stays in place and we can do our grinding without a third hand. And now when I spin the workhead, you see what's going to happen. I'm going to spin this. I will probably just go back and forth and not continually spin it. And I will at the same time feed the grinding wheel this direction against the tool. Okay, as you can see, now we ground this eccentric shape. I didn't go to a full circle grind. A little bit of the original surface out here is left, but that doesn't matter. Now we need to split the front here in half so we can create a cutting edge. This orientation that we started out with the relief grind on the left side, that's also the orientation how it's going to be used later. This is 0, so we unlock the workhead and we turn it 90 degrees left to 70 in this case, lock it, and now we will grind the front here in half. Basically the same thing that we would do if we grind a D-bit. Okay, as you can see, grounded in half, and with a boring bar it's not as important as with a D-bit to hit half the diameter very exactly. In fact, it's very uncritical. Next step will be to grind the side relief to the back and down. So we rotate it back in our starting position, so it's the flat we grind is horizontal. Now we set our relief angle down, something like, all the angles are not very critical, something like 10-15 degrees is perfectly fine in this case. We set it down here by loosening this joint, swinging it over 15 degrees. And we need some back relief. That means we need to swing this over here. This joint needs to go beyond 0 degrees. This doesn't work. There is a pin down here that sets the 0 degree stop. When we reach down here and we pull this pin out, we can go past 0 degrees. Doesn't need much. 2-3 degrees of back relief are perfectly fine. Plenty enough. And now we just need to go back into our work envelope here, bring it back into a place where we can use it. There we go. Lock everything, and now we just feed the tool against the wheel. This usually doesn't need very much, just so this relief flat here meets this top surface here, and we get a perfect sharp intersection here. And the only thing left to do is to do the same to the front of the cutter. To grind the front of the tool, we get our vacuum attachment out of the way. We do not need as much clearance to the bottom on the front as we do on the side. We can drop that back to 7 degrees. 6-7 degrees is a good value. And we need to move this over, and we swing this 90 degrees against our stop pin. Stop pin is in the way again. And we pull the pin again, and we go a little bit past 90 degree. Like this. Lock it. And we keep this at 0, of course. And then we get it again into the area where we can use it on the grinding wheel, or bring it in contact with the grinding wheel. Just like this. With grinding carbide, dust extraction is really a good idea. The carbide dust is not only bad for you, gives you cancer and kills you over time, but it also is really bad for your machinery. Carbide dust gets into sliding surfaces between ways and stuff like that, and it wears down like crazy. It's like a lapping compound, dry lapping. Okay, there we go. That's a basic boring bar for ID boring against a shoulder, internal shoulder, completely ground from solid on the D-bit grinder. Next step would be to change the wheel from, this is a D125, against a much finer D40 or D40, yeah, this is a D40 lapping wheel. This is also a diamond wheel, a resin-bound diamond wheel, but it's incredible fine. And this leaves a finish that's good enough for a scraper, but also almost mirror-like finish that you would find on a high-quality cutting tool, lathe tool that is. So I'm set up for a test cut. This is a piece of 12842, aka O2 tool steel. I have one of the boring bars I ground set up here in the tool post. It's on center height. The flat here is horizontal. Usually it's good enough to just eyeball them. If you're very picky, you can indicate them in. It's exactly on center height. Running at 1200 RPM and a feed of 0.07 millimeters per rev. Taking a depth of cut of 0.025 millimeters, just to see if it can take a very fine cut. And as you can probably see, surface finishes is darn good. Especially if we consider that this tool has no corner radius. If we add a little tiny corner radius with a diamond hand lap, finish would even increase, but corner radius increases the cutting pressure on the other hand, because the chip width gets larger. The chip gets thinner, but at the same time it gets wider. It's always a little bit of trade-off. I like my tiny boring bars with a sharp edge, if possible, if the part allows it. If you have to have a corner radius on a hard internal shoulder, there's no option. You have to use a corner radius. But these work really very well, and that's my go-to solution for quite some time now for small diameter ID boring. Takes 5 minutes to grind one up from scratch, and then I just put them in a drawer, and when I need it again, I might have one that fits. And that was a dry cut without lubrication at 0.1mm depth of cut. These small boring bars without a chip breaker or positive rake tend to produce a very stringy chip. In this case it went into the spindle bore and just migrates to the other end. With large depth of cuts, these tend not to work very well. But that's not their main purpose, because they're for small diameter work, for precision work. And as you can see, the finish in the dry state is even better. Very, very good finish. Let's take one last cut with a depth of cut of 0.5mm. We will decrease the feed a little bit. And even at 0.5mm depth of cut, 1mm in diameter, left a very decent finish. As you saw, the chips get really annoying and stringy in that case. And this was 1mm depth of cut. It works, doesn't chatter at all, takes a decent cut. You can see the matte finish here are the first 3mm where I did a dry cut, and then I added some coolant, and then it gets nice and shiny back here. Not the best tool for heavy roughing, but for precision work they work excellent. Robin said he showed on Instagram a version of these that have a helical grind, and I might try to figure out how to grind them yourself using either the bit grinder or tool and cutter grinder. They have the benefit to have a positive rake, highly positive front rake, and you also grind them only on the front face. So they should cut even freer than this one, and should be possible to grind them yourself from solid. But I have to figure out the geometry in CAD before that. Okay, here we are in CAD, and I modeled up basic version of the boring bar. As you can see, we have the shank here highlighted in yellow. We have the eccentric relief grind here, and we have the cutting section in front here. And the way I figured out how large the eccentricity has to be, I just went in this model and I changed the value of the eccentricity. I can do this here, just down here. This is this 0.75, that's the current eccentricity. Let's change this to 0.2 millimeters. As you can see, then we have a way smaller eccentricity, a smaller relief grind here. If we change eccentricity to, say, 1.5 millimeters, which is a very large amount, we end up with this. This would work too, kinda. We have very much relief for the chip here, really a lot of space for the chips to go out here, but as you can see, the remaining shank diameter here is very small. This is 3 millimeter in diameter. That's not very stable. So I played around, and 0.75 gave me a decent result that looked good from the proportions and also has plenty of room here for the chips to not get catched between the wall and the shank. So I hope I confused you enough and gave you some ideas what you can do with D-bit grinder. Thank you all for watching, and see you next time.